In the previous lesson, you learned how electrodes for lithium-ion battery cells are fabricated, and in this lesson we continue to discuss how the remaining parts of the fabrication process proceed. This process might be performed on a machine like the one shown in this illustration here. The cell assembly process involves steps such as building the electrode subassemblies and putting these subassemblies into packages and filling the cells with electrolyte and performing some final operations of making sure that the package is sealed and perhaps welding the container and inspection of the cells. Some of the details of how this is done vary depending on whether we are talking about building a prismatic or a cylindrical or a pouch cell, but many of the details are fairly similar. And this illustration shows the process as it would apply to a cylindrical cell or even to a prismatic cell. In this drawing, you can see that the foils are already coated with the calendared electrode materials produced from the previous steps, and these foils are mounted on the left side of the machine. The foils are then unwound from the large roll, and they're passed into a machine that winds these foils into either the cylindrical shaped jelly roll or the prismatic shaped flattened jelly roll shape. The strips are then cut to the desired length to separate the jelly roll from the electrode foils that come into the machine, and the jelly rolls are placed inside empty metal cans, which are the containers for the cells, and then these metal cans are then welded closed except for a small opening. Electrolyte is added into this opening, and then the final sealing of the cell packaging is done by welding it closed. The cell is inspected, and the packaged cell is sent off to the next process in its assembly, which is a formation process, and we'll talk about that later on in this lesson. Several of the details in the process that were shown on the previous slide are different depending on whether a pouch cell or a cylindrical or a prismatic cell is being constructed. So here we think about pouch cells. Pouch cells are often used for high-capacity battery applications because there's very little wasted space inside the packaging of this cell. And furthermore, the cells are basically rectangular in shape themselves, and so there's very little wasted space when we put multiple cells together to form a battery pack as well. Pouch designs start with electrodes fabricated in the way that you saw in the previous lesson, and then the electrode structures are stamped out of these reels of electrode material in the shape as shown on this slide, of basically a rectangular structure with a tab coming out of that structure that will be eventually connected to the cell terminals. So these individual electrode structures are stacked on top of each other as shown in this illustration. So, for example, we might start with a separator material and stack on top of that a positive electrode material, and then a separator, and then a negative electrode. And that whole subassembly would be repeated multiple times so that there would be many negative electrodes and many positive electrodes overall inside of one pouch container. The separator may be cut or stamped to essentially the same size as the electrodes, probably a little larger so that there would be some extra space around the edge to make sure that any shifting of the packaging did not result in a short circuit. Or alternately, the separator could be wound in kind of a zigzag shape between the different electrodes of different types that would give further assurance that there would be no possibility of short circuit if the electrodes actually shifted in the package. Notice in this diagram that the negative electrodes have their current collectors coming out of tabs on one side of the drawing, the top right in this case, and the positive electrodes all have their current collectors coming out of the same place, the bottom right of the drawing in this case. All of these individual negative electrode current collector tabs are welded together, and the positive electrode tabs are also welded together to make one large cell out of these individual small cells by putting them effectively in parallel electrically. And so we have one virtual large negative electrode and one virtual large positive electrode that are the sums of the areas of the negative and positive electrodes themselves. And then these two welded current collector tabs are themselves welded to some kind of a tab that extends outside of the cell packaging and forms the overall cell negative and positive terminals. Cylindrical and prismatic cells are formed in a different way. For cylindrical cells, the negative and positive electrode foils are cut into two quite long strips, and then one of the electrodes is placed on top of a separator, which is placed on the other electrode, which is placed on a separator, and this overall long subassembly is wound around a small diameter rod, a metal shaft. And the shaft is usually removed when the cell is packaged, leaving a really tiny cylindrical vacancy right in the center, actually. The electrodes ultimately end up with a structure that's shown on this diagram, where you can see that a spiral forms from concentric layers of negative and positive, negative, positive, all separated by the separator materials. The prismatic cells are constructed in a very similar way, but the winding is done around a flat, thin flat mandrel instead of around a cylindrical mandrel, which makes for an overall flatter package that's inserted into a prismatic can instead. To connect to the outside world, these current collectors that are cut long have little tabs at different locations that come outside from them as well. And so one or more tabs from the positive electrode are welded to the positive terminal of this cell, and one or more tabs from the negative electrode are welded to the negative terminal of this cell. If the purpose is to construct a high power cell, then there are often multiple tabs per electrode that are welded to external terminals in order to allow more current paths and therefore more uniform utilization of the electrodes. Whether we are constructing a pouch or a cylindrical or a prismatic cell, the next step involves filling the cell with electrolyte in any of those cases. We add our safety devices like internal fusing, for example, first. Then we insert the subassembly into the package, but at this point the cell is completely dry. The package is sealed except for a small opening, it's often sealed by laser welding. For a pouch cell, it could be sealed by heating some materials and effectively making a hot glue connection. But after this initial sealing process, we still leave a small opening through which we will insert the electrolyte. This is done in a very interesting way. The cell is first subjected to a vacuum through this small opening, which removes most of the air from the inside of the cell, from the pores in the porous electrode structure. And then a small amount of electrolyte is injected into the cell, and then the vacuum is released so that the atmospheric pressure forces the electrolyte into this cell and into those small pores and small pore openings. This can be done multiple times so that the electrode porous structure is filled as full as possible with this electrolyte. It's interesting that even at this point, the cell may not be completely wet with the electrolyte material, and it may take several charge-discharge cycles for that to happen. And so it's not uncommon to see the first several cycles of a brand new lithium-ion cell appear to increase in capacity as this electrolyte makes its way into all of the pores and then allows the lithium ions to flow to all of the solid active material. And then after these initial cycles where the capacity appears to be going up, then it starts to go down as this cell ages. In any case, after we have filled the cell with as much electrolyte as we're able to, we seal the remaining opening using, for example, a laser weld or some kind of a heating process. The electrolyte fill operation must be done in an environment known as a dry room. A dry room uses a very high capacity dehumidifier to remove as much moisture from the atmosphere as possible. And this is really important because the electrolytes used in lithium-ion battery cells often have salts that react chemically with water. So any moisture in the electrolyte will cause the electrolyte to decompose, and this can cause them to emit toxic gases. And furthermore, lithium hexafluorophosphate, or LiPF6, which is one of the most commonly used electrolyte salts, reacts with water and forms toxic hydrofluoric or HF acid when it does so. And this HF acid can cause the electrode materials to dissolve or disintegrate inside the cell over time, which leads to capacity loss. So we highly desire to avoid that, or at least to minimize that. And we do so by injecting the electrolyte into the cell inside of a dry room environment. So at this point, the cell is completely constructed, and some remaining tasks might include things like printing a cell serial number on the cell and maybe some other identifying information on the packaging. But now the cell is ready for its very first charge. Before we discuss this charging process, it's important to talk a little bit about something that's known as the solid electrolyte interface layer in a lithium-ion battery cell, otherwise known as SEI. It turns out that when lithium intercalates into graphite in the negative electrode, the lithiated graphite reacts with solvents in the electrolyte and forms this SEI layer, the solid electrolyte interface layer, which is a film coating the particles of the negative electrode. This process of SEI formation and growth consumes lithium, so it results in capacity that's lost. The film also impedes ions, lithium ions, that want to travel from the electrolyte into the electrode and vice versa, which results in a higher resistance for this cell and therefore results in a power loss. And neither of these is desirable. But on the other hand, this SEI layer also turns out to stabilize the graphite against further reaction with the solvent, which is a positive feature. So it tends to be a self-limiting reaction. When the lithium-ion battery cells are assembled, they are done so in a fully discharged state at 0 volts. All of the lithium begins in the positive electrode. The negative electrode is pure graphite with no lithium in it whatsoever. So at the beginning point of the manufacturing process, no SEI has formed. But when we build this battery cell, we must put it through at least one precisely controlled charging process. And during this first charging process, the graphite is lithiated for the first time, and this causes this chemical reaction that forms the SEI layer. And because of this formation of an SEI layer, the first charging process is called the formation process. We would like this SEI layer to be as thin as possible because we don't want to have excessive capacity loss. We want it to be as uniform in thickness as possible so that it doesn't easily break down at a later point in time. And this is most easily achieved if we form this layer slowly. So we form the layer by charging the cell very slowly for its very first time. And then after that, it may turn out to be valuable to gently charge and discharge, otherwise known as cycle, the battery cell a few times to stabilize the SEI layer before this cell is delivered to the consumer. If the formation process is badly done, then this SEI layer will be thick and non-uniform, and it may be brittle, and it may easily break down as the battery cell is being operated in the consumer application. anytime the SEI layer breaks down, it exposes more graphite to the solvent, and at that point the solvent will react to the graphite and form additional SEI products, which will reduce capacity and increase resistance. So while the SEI layer is formed for the first time when we charge the battery cell for the first time, it actually does tend to grow somewhat over time due to failure of the existing SEI layer and building of additional SEI layer. So good battery cells are formed, have a formation cycle that produces a good SEI layer. And the difference between a good battery cell and a bad battery cell might be your manufacturing edge when you're trying to market your cells to the consumer. And because of that, the formation processes used by different manufacturers are proprietary. They're trade secrets. Most likely the manufacturer does not do a normal constant current, constant voltage charge, and the process used may take several days or even several weeks and may include steps that hold the cell voltage constant for periods of time at different voltage levels. They may rest the cell at different open circuit conditions for different periods of time at different temperatures and so forth. And for this reason and for other possible variations in the processing steps we've seen throughout this week already, cells from different manufacturers can have very different operating characteristics and especially life characteristics, even though they share supposedly the same chemistry. The way the cell is manufactured has a critical influence on how long that cell will last in the application. And so having tight controls on the manufacturing steps is very important to be able to create the best cell possible. During this formation process, cell performance data are gathered and recorded in order to be able to perform some quality analysis. If we notice during formation that a cell has a high self-discharge rate, that points to some manufacturing defect, and that cell will be recycled. It will not be sold to the consumer. If the cell has capacity that's very different from what's expected or has impedance that's higher than what's expected, that could indicate that there's a manufacturing process that's not under control, and that will lead to a lot of creative detective work to find and correct the process that is causing this problem. Many times, even when cells do have parameters that fall within the desired tolerance band, the cells that come out of production are sorted into different lots according to their capacity and resistance, so that different lots of cells can be matched to each other for certain applications that require all of its cells to have very close capacities or resistances and so forth. And this process is called matching, or sometimes binning, as you put cells in different bins, so that the cells could be used together in this type of high specification environment. All of this testing, by the way, is done inside the manufacturing facility, including other quality control measures that I have not even mentioned in every step of manufacture. And we strongly desire that all of the manufacturing defects are identified either before or during formation and not after formation. Certainly not after the battery cells have been sold to the consumer and battery packs have been assembled and it's in some product. So in order to avoid a low yield, it's important to enforce tight tolerances and strict process controls. We need to avoid contamination of the raw materials. We need to avoid physical damage. We need to avoid things like burrs, the sharp edges on the electrodes, because all of these are extremely dangerous and can cause serious problems when the cell is in operation. In order to reduce contamination, cells are normally manufactured in a clean room condition similar to what's used when manufacturing semiconductor parts. So to summarize this lesson, you've learned that cell construction comprises building the electrode subassemblies first, then packaging them, then filling the package with electrolyte, and then sealing and welding and inspection. After construction, the cell undergoes a precisely controlled formation cycle to charge it and to grow a thin, uniform layer of SEI. A byproduct of this formation cycle is that we can measure a set of data that enable us to perform acceptance testing and even binning or sorting of cells for highly calibrated applications. And finally, the cells are put in boxes and they're shipped to the end purchaser of the cells. This is usually done at a low state of charge to a middle state of charge range so that some of the degradation processes that we'll look at later this week will be minimized, and so that the energy stored in this cell is also at a fairly low level in case some safety event happens during shipping. So at this point you've learned how lithium-ion battery cells are manufactured and how they are put into their packages and the formation cycle and so forth. What we're going to look at for the rest of the week is the other end of the life spectrum. Here we've seen the beginning of life, but what causes a cell to age and degrade and break down, and what are the consequences of these aging mechanisms? And so that's what we will look at next.